Okay, welcome again. So, this will be our last session on Scilab. So, the last session we want to do Fourier transforms and Laplace transforms. These transforms are very useful in not only mathematics, but in a lot of science and engineering. In fact, you may have heard that there are now FT NMR spectrometers and FT IR spectrometers. So, the Fourier transforms are extremely powerful to convert data from say time domain to frequency domain or from your spatial variables to your momentum variable. These are very good and they have huge number of applications. So, basically these transforms are nothing but integrals. So, I want to define these transforms and discuss how to calculate these using the programming, including the Scilab programming. So, let us see the definition of Fourier cos and sine transform. So, a cos transform f c k is defined as square root of 2 over pi integration 0 to infinity f x cos k x dx. What this does, suppose you have a function f x, it multiplies that function by cos k x and integrates from 0 to infinity to give a result which depends only on k now. When x is integrated out, the result will be a function only of k. So, that is a cos transform. So, f c of k is the cos transform of f x. Now, f x is the inverse transform of f c. So, you have a forward Fourier transform going from f x to f c of k and you have an inverse transform to go from f c of k into f x. This is an inverse transform. So, really speaking, when you do the inverse transform, you should get the original function f x. So, this is a cos transform. So, in place of cos, if you put the sine, it will be a sine transform. Okay. So, you have a cos transform and a sine transform, but the more general is the exponential. Remember, e to the I k x, I can write it as cos k x plus I sin k x. So, this exponential e to the I k x is a sum of cos and sine. So, this exponential transform is really a sum of cos and sine transform. So, how is that defined? F of k, now this is the Fourier transform, not the cos transform. Fourier transform is 1 over 2 pi minus infinity to infinity f x e to the I k x dx. So, this is my forward transform, and when I do the inverse transform, the sign is changed here. You see, I had minus I k x, so here will be plus I k x. So, this is my inverse transform. So, for many functions f x, these transforms have been calculated and you will find several tables of Fourier cos and sine transforms. I will just give one example here. Okay. In this example, I have given several examples of Fourier transform pairs. What is the meaning of transform pair? If I take the function f x, take a Fourier transform, you will get f of k. When I do the inverse transform, I get the original function. So, exponential of minus a x, the cos transform is a by a square plus k square, the inverse transform is e to the minus a x. So, suppose I take a Gaussian function, one of the interesting thing is that the Fourier transform of a Gaussian is also a Gaussian function. Remember, I have e to the minus a x square, a greater than 0, its Fourier transform is e to the minus k square by 4a. When you inverse transform e to the minus k square by 4a, I will get my original function e to the minus a x square. Now, this is sine transform. Sine transforms are a little different because sine is an odd function and cos is an even function. So, these are different. So, finally, this is a list of Fourier transform. Okay. I have taken Fourier transforms of 3 functions, their inverse transform. So, you will in literature you will find a large number of data points. Now, before I go into some applications, let me go back and suppose now I want to evaluate this. If I want to evaluate this using the programming technique, now we are all fairly good at evaluating integrals. So, how would I evaluate? I just discretize f x into a large number of points. Suppose I have 1000 values of f x, multiply by cos x and I can integrate using trapezoidal rule or Simpson's rule. But the main point is when x becomes large, if f x becomes very large, then this will not converge. So, what is the meaning of convergence? The integral should give you a finite value. Okay. So, for convergence there is a requirement that at large values of x, this fx should go to 0. If it does not go to 0, you will have a divergent integral. So, you can do this Fourier transform only for certain specific functions. Okay. So, that should be borne in mind. So, now let me go to some applications. What are some very, very useful applications? As I mentioned, FTNMR, FTIR, the Fourier transform have great use in signal processing. So, electrical engineers, I can almost say that you cannot study electrical engineering if you do not do Fourier transforms. This may be an overstatement, but fairly true. So, now these transforms are useful in solving differential integral equations as well. So, I will give you one example. So, what this slide shows you, it tells you the Fourier transform of a convolution. So, G is a convolution function f star h. This convolution means, look at this particular line. Convolution function is, you have a function f of t, you multiply by x minus t, okay, and integrate, okay, so that you have only one way. This is called a convolution. Whenever you have f of t and h of x minus t, integrate with respect to dt, d tau. So, it is a convolution function. So, what we are showing here, the Fourier transform of a convolution, the Fourier transform, this GU is a Fourier transform of a convolution. Okay. So, the Fourier transform of a convolution is nothing but the product of the Fourier transforms of G and H. So, this is very useful because whenever you have equations involving convolutions, you can convert them into products of Fourier transform by taking a Fourier transform, and when I take now an inverse transform, I will get the inverse transform of the convolution. So, this is very, very useful. Okay. So, convolution in the spatial domain will give you multiplication in the frequency domain. Here u is a frequency. So, a very complicated problem in the spatial domain gives you a very simple multiplicative problem in the frequency domain, and hence they are very, very useful in solving these kind of equations. So, I will now next consider Laplace transform. Many of you may have been familiar. A Laplace transform of function of t is nothing but 0 to infinity e to the minus st f of t dt. The Laplace transform has a multiplicative factor e to the minus st. For a Fourier transform, it was e to the minus ik. So, Fourier transform has a complex exponential. So, this is a real function now. This is a Laplace transform of a function is given by 0 to infinity e to the minus st f of t dt. So, this is an example. Suppose my f t is a constant function. If the function is constant, the Laplace transform of that constant is 1 by s. Now, instead of a constant function, if my function is e to the minus t square, so this, if I take a Laplace transform of e to the minus t square, it will go to infinity because I have e to the minus st and e to the t square. E to the t square is a very rapidly increasing function. So, I will have a divergent Laplace transform. So, just that I had Fourier transform pairs, I can have Laplace transform pairs, and I will show you one application of use of this Laplace transform. Suppose you want to solve this differential equation with some initial condition. This is a second order derivative d2y by dt square plus y equal to 1, y0 equal to 0, y prime equal to 0, equal to 0. I want to solve this. How do I solve it? Take the Laplace transform of this equation. So, Laplace transform of y double prime, second derivative, Laplace transform of y is equal to Laplace transform of 1. We already saw in the last slide that Laplace transform of 1 was 1 by s. Now, there is a formula for Laplace transform of the derivative. The Laplace transform of the derivative is s square Ly minus sy0 minus y prime 0. Okay. So, substitute y0 and y prime 0. So, you will see that your Laplace transform of y is 1 by s minus s by s square plus 1. So, when you take an inverse transform, you will see that your y is equal to 1 minus cos t. Okay. So, that is how equation which was very complicated is a derivative. It is now written as an algebraic equation. Now, algebraic equation you can invert to get your final solution of y. From the Laplace transform of y, which was this, you invert it, you get the function which is a solution you got. So, this way you can use Laplace transform as well as Fourier transform, but our present aim now is to really use Scilab to calculate this Fourier transforms. Okay. So, here is my program. So, I am going to calculate what is called a DCT. DCT is discrete cost transform. So, what we discussed so far was continuous. What is the meaning of continuous? It takes all values between 0 and infinity. For a discrete Fourier transform, they will take only discrete points. See, we cannot do an infinite integral using a computer. So, what I will do? I will just illustrate calculation of a discrete cost transform of a function. So, what is my function now? So, let me define a function. So, this is what I am going to define. AI is my function, okay. My constant is 1. So, I want to determine 512 points of the function A. So, what is my function? It is defined here, okay. C is equal to 1, n is equal to 512, space x, this is the spacing in the x axis, it is 0.01, PPI is percentage PI. If you recall, we said that percentage PI is nothing but the value of pi. So, that I have equated to PPI. So, I do not call it PI because PI there will be confusion. Already percentage PI is a 3.14. So, I will define a new variable and equate it to pi. Now, for I going from 1 colon n, remember this colon not comma, okay. For I going from 1 colon n, my xi is I minus 1 into space x. So, 0.01 is my spacing, that means the first value is I minus 1 will be 0. So, 0 into space x is 0, my first value of xi is 0, second value is 0.01, third value 0.02, fourth value 0.03. This way I determine xi values for 512 points, and my A function now is nothing but e to the minus c into xi square. This is a Gaussian function. This is a Gaussian function. I want to take a discrete cost transform of a Gaussian function. So, what I will do? I will copy paste all these things. I will copy paste these functions and go to Scilab. Okay. So, I will just copy paste. Okay. I have executed. Now, I can plot this function A. Okay. So, let us say plot into bracket A. Okay. So, it will plot. So, it has plotted this Gaussian function. It has plotted this Gaussian function which is e to the minus x square. Now, I want to take the Fourier transform of this. Okay. So, if I want to take a discrete cost transform, I need to know what is my discrete cost transform. So, how will I find out? One way would be to go to the help file. Remember Scilab, one great thing in Scilab is it gives you a help browser. Okay, let us locate the. So, there is a help browser. Okay. So, this is a help browser. So, I just typed help in Scilab. DCT is a discrete cost transform. So, this is the sequence now. So, this help tells you how to do the discrete cost transform. So, you will see that this is the description. Okay. There are several ways of doing discrete cost transform, DCT1, DCT2, DCT3, DCT4, so many are there. So, what we want to do? We want to calculate this DCT, discrete cost transform. The algorithm is this. I hope you can see it well. Let me make it a little larger. The algorithm is the transformed variable is k. Okay. So, I get x k equal to omega k into ai into cos pi into I minus half into k minus 1 divided by n, k going from 1 to n. This omega 1 is 1 by root n for first value, and for other values it is 2 by n square root. Okay. So, this is my discrete cost transform. I can do it in two different ways. What are the ways I can do? I can do the discrete cost transform through my comments. You see, these are what I have done here. I have written my own program to calculate the discrete Fourier transform. Remember, there was a square root of 2 by n, square root of 2 I going from 1 to n, sum equal to 0. This factor is pi into k minus 1 by n, and then the integrand was ai into cos of I minus half into k minus 1 divided by n into pi. So, I have exactly calculated this f t by my own program. I did not use the Scilab discrete Fourier transform, I use exactly my own program. So, what I will do, I will copy these commands. So, I have calculated A, so I will copy paste all my own. Okay. I will what I have done, I have written a Scilab program exactly like this Scilab algorithm. Remember, this was my Scilab algorithm. So, I shall use the Scilab algorithm as well as my own expression of the same algorithm and show you the calculations. Okay. So, now I do not need this help command anymore. So, I shall close the help command. So, I will go here, I will paste. I made a mistake, I should paste it. So, I copy, I paste it. Okay. So, it gave some warning, that is okay. So, it has calculated, let us see. Okay. So, this is my exponential original function. So, I want to now see how the Scilab, I shall knock it out. So, I shall plot, okay. I will just plot f t. So, let us see. Okay. So, this is my Fourier transform calculated using my program. So, let me also calculate the Fourier transform discrete cost transform using the Scilab. Okay. So, let me close it. My function was A. So, I will say now B equal to dCt, this is a direct cost transform into bracket A. Okay. So, f t was the Fourier transform I calculated using exactly the algorithm in the Scilab. Now, I will calculate using the discrete A comma 1. So, I am using this comma 1 because it is a forward transform. Remember, there is a forward transform and a reverse transform. So, my B should be the discrete cost transforms of a forward direction. So, let me calculate. So, it has calculated. Now, plot B. So, you will see this is the discrete cost transform calculated using the Scilab. This is exactly what we calculated as f t. Our f t and the Scilab B are identical because they use the same algorithm. So, now what I want to do? I want to calculate the inverse transform. So, what is an inverse transform? So, I had A and I have got B, which is a forward transform. Now, let me say C is equal to equal to dCt of B comma minus 1. So, minus 1 is my inverse transform. Okay. So, I have a forward transform which is B, inverse transform is C, C is the direct discrete cost transform of B, inverse minus 1. So, let me do this C. Okay. So, I have calculated C. Now, C was the inverse transform. So, let us say plot, let me plot C. So, we will see that this is my C, which is really an exponential function. Okay. So, this is, so my forward transform was B, my inverse transform is C. So, you see that I got this original function. C is the inverse transform of the forward transform, I am getting exactly the same as the original. On the same graph, let me also plot A. So, I now plot A on top of C. Okay. So, let us see. Okay. So, there has been no difference. Okay. There has been no difference. So, what did I do? I started with a function A, which was a Gaussian function, took the forward cost transform, took the inverse cost transform, and I got the original function. So, what I have done so far is to discuss Fourier transforms as well as Laplace transform, told you how it is so easy to calculate Fourier transforms using Scilab. It is just you define the function and use dCt for direct cost transform, and for sine transform maybe it is dSt for. So, there are other ways of doing it. They are called fast transform, fast Fourier transform, FFT, again one for forward transform. -1 for reverse transform. So, you can in your exercises you can see the table that I had given. I had given you a table of forward transforms and then practice using this Scilab software. So, this now concludes my discussion on application of Scilab. What I will do now, I will start discussion on molecular dynamics simulations. So, this is our main application. I will close all my Word file. My main thing here was how to apply computational chemistry to actual chemical calculations or problems in chemistry. So, what I want to do, I will begin now discussion on classical molecular dynamics calculations. So, this is what we are going to do for the next 3 or 4 hours using our own program. Then after some time we shall use GROMACS program. So, I shall begin now classical molecular dynamics simulation. This is going to be my outline till the end of this course. Up to now we have done lots of numerical methods, wrote Fortran programs and executed those programs. We also did elementary programming before we did the numerical methods. Then I used Scilab to illustrate most of the things that I demonstrated using Fortran programming. The only thing we did not do was to write a program for finding the diagonal values of a matrix. We just had a very simple program for diagonalization. What I will urge you, you go to that numerical recipes, look at some standard routines for matrix diagonalization and try to use it in your own Fortran program. Of course, diagonalization using Scilab is very easy. It is just a one line command lambda, you know that lambda comma b is equal to b diagonal in your matrix A. So, now I begin classical molecular dynamics. So, what is that outline? I will first introduce what is classical molecular dynamics, then consider all the systems that can be studied. Okay? And basically we want to know how this classical molecular dynamics can be used to do several useful calculations in chemistry. This classical molecular dynamics very strongly depends on the intermolecular potentials. So, it depends on the intermolecular potentials, and once we have the intermolecular potentials, I will be solving the equations of motion. Okay. Normally, we will be using classical molecular dynamics. That means, I am going to use classical equations of motions, which are Newton's laws or equivalent forms such as Lagrange equations, Hamilton's equations and so on. So, in classical molecular dynamics, a very important concept is a periodic boundary conditions. The reason we use periodic boundary conditions, the number of particles you can use in classical molecular dynamics is going to be limited into tens, hundreds, thousands or 10,000s. You cannot use infinite particles, because if you use infinite particles, your memory requirement would be infinite and you can do very little. So, you will use a finite number such as 100 or 1000. So, a finite set will not represent a liquid, it will only represent a box or a droplet. So, to make your calculation agree with bulk liquids, I have to use periodic boundary conditions. We will describe that in sufficient detail. Then even in addition to periodic boundary condition, there is what is called a minimum image convention. We will discuss this in a later slide. Then in addition to classical molecular dynamics, we will also be doing Monte Carlo simulations, Monte Carlo algorithms. These Monte Carlo algorithms use the random numbers which we have already discussed. We discussed two types of random numbers, linear random numbers or uniform random numbers between 0 and 1. We also consider random numbers which are Gaussian in nature. So, both those random numbers algorithms are used in Monte Carlo calculations. Then using these algorithms, what we do is we generate a trajectory. I will describe what we mean by a molecular dynamics trajectory. Then after you do molecular dynamics simulations, what you are going to calculate, these are called correlation functions. There are different kinds of correlation functions which are of use in chemistry. They are spatial correlation functions and time correlation functions. Then we will calculate diffusion constants. The diffusion constant tell you how the particles in a liquid diffuse. Then after describing all the theoretical framework, we will execute two sets of programs. One is our own program written in Fortran, and then we will also describe a public domain software GROMACS, which is a very powerful software and you can apply to many systems of interest. Okay. So, now let us see what are the main features of classical molecular dynamics. The main features of a classical molecular dynamics are, the classical molecular dynamics tries to solve classical equation of motion, classical equations of motion. You want to solve this equations of motion for atoms and molecules of the system. So, take a system containing atoms and molecules, you solve the equations of motion to obtain their time evolution. We are going to evolve the system as a function of time. So, that is why it is called dynamics. Dynamics because how things move as a function of time, and we want to apply this to many particle systems. Okay. So, what is a many particle system? Many particle system is anything more than 2 particles is many particles. Okay. So, once you have more than 2 particles, say 3 particles, 4, 5, a general analytical solution is not possible. You do not have an exact solution with a formula. Okay. Just as you have a formula for 2 particle motion like a hydrogen atom or an earth and sun moving together, one is a classical system, one is a quantum system. So, for 2 particles there is an exact solution, for 3 or more there is no exact solution. So, you have to use numerical methods. So, that is how whatever we did in our course, all the numerical methods that we used in our course will now be extremely useful in solving these problems of real interest. As I mentioned again, we will be discuss only classical mechanics, because if you want to discuss many particle time dependent quantum method, it is very difficult. The time dependent quantum method involving the Schrodinger equation is much more difficult than classical molecular dynamics, and classical molecular dynamics gives you fairly accurate results for certain systems. So, we will also see which systems we can study and what are our algorithms for classical molecular dynamics. And the main thing would be, after you do classical molecular dynamics, you study the time evolution, you will average over all the results of your simulation. Okay. It is called time averaging. You average to get thermodynamic and kinetic properties of the system. So, the goal is your thermodynamics and kinetics, your technique is molecular dynamics, and in the next lecture we shall let us see. Okay. I will just, before I conclude, let me give you examples of systems that can be studied using molecular dynamics. One set is simple liquids, atomic systems, ionic systems, molecular liquids and their mixtures, ions and hydrophobic particles in solvent mixtures, macromolecules, biopolymers, membranes, reactive media. So, all these systems can be studied using molecular dynamics. So, in the next lecture, I will be discussing several algorithms that are useful in molecular dynamics. So, to summarize what we did today, we use Scilab to do Fourier and Laplace transforms. Laplace transform I will leave it as an exercise. Go to the Scilab website, look at the Laplace transform, how to use Laplace transform. Fourier transforms I have already told you how to do it using your own program as well as using Scilab. I introduced classical molecular dynamics, and in our remaining lectures in the course, we will be discussing several aspects of molecular dynamics and Monte Carlo simulations. I will close here. Thank you.